So yesterday we looked again at power series functions. So we're into this section now, this later part of section 4, which is looking at various applications of the derivative. Yesterday we looked again at power series. We'd already encountered power series when we were doing series of real numbers back in chapter 2. But we looked again at these, and we did some kind of modification or semi-justification for the Taylor series. And we showed that if a function is differentiable, then and it has a power series, then the only power series it has is the Taylor series. So for functions that are differentiable as many times as you want, they do have a power series, and it's unique, and it's given by the Taylor series. So the coefficients of the power series are these coefficients here, depending on the various derivatives of the function evaluated at the base point. We did a couple of examples, messing around with the exponential Taylor series and the sine Taylor series, and did a bit of computer verification of that. So that's there yesterday. The recording is there yesterday, and there's a link from the recording page to the little snippet of code I was using and that. So you can make use of those. So today I was going to look at another example, which is about stationary points of functions. Okay, so you may be familiar with this already from your previous studies, but we'll look at it again. And I've got a couple of there's a good few exercises concerning this at the end of chapter exercises, so I think we'll do a couple of those as well. Okay. So what do we mean by a stationary point of a function of a single variable? Well, we mean a point, well, in terms of its graph, we mean a point where the tangent line to the graph is flat, is horizontal. Okay. So for instance, there's a couple of graphs, and there's a couple of highlighted points there. The top one we call a minimum, or a local minimum of the function. Within this small window in that top graph, that highlighted point there is the point where the function takes its minimum value. And underneath it, we have illustrated a maximum point, or at least a local maximum point. The portion of the function's graph that we're seeing there, that point there highlighted in the second picture, is the point where the function takes its maximum value within that range that we can see the behavior of it anyway. Okay? So these are what is known as stationary points. So you can characterize them graphically in terms of the graph by saying they're the points where it reaches a local maximum or local minimum value, or equivalently in terms of the tangent line, it's where the tangent line has slope 0, where the tangent line is horizontal. And there's a third possibility, which are called these points of inflection, where it's kind of like a minimum if you look at it to one side, or a maximum if you look at it to the other side. Kind of a mixture of being a maximum and a minimum. These are called points of inflection. And if you think about what the tangent line is looking like there, you see the tangent line is horizontal there at that highlighted point. It's got slope 0. Now, tangent lines, or the slopes of tangent lines, is given by the derivative of the function. So in terms of the function and derivatives, a stationary point is defined as a point where the function has derivative 0. Okay, so if y is given as the functional, if y is a function of x given by the function f, say, then a stationary point of f, or a stationary point of y, is given by any point, any value of the argument x that makes the derivative 0. Okay. So we have these three different types of stationary point. So we'd like to describe, so they all have the property that the derivative is 0 at these points. The local minimum, the local maximum, and the point of inflection. So we'd like to be able to describe the difference between the three types, and be able to say when a type is of one type or another. Okay. And that is done by examining the behavior of the derivative, the derivative more closely. If you think about the local minimum point, so at the local minimum point itself, the derivative is 0, fine. But how is the derivative behaving either side of the local minimum? Well, to the left of it, when you go to arguments less than the minimum point, because it's a minimum point, to the left of it, the function is decreasing. As you move from left to right, the function is decreasing. You go through the minimum point, and then as you continue to move left to right, the function starts to increase again. Now, the rate of change is given by the derivative. So that means to the left of the point, we've got negative derivatives, because you've got decreasing behavior. And to the right of the point, we've got the derivative is positive, because you've got increasing behavior. Okay? So the sign of the derivative changes from negative to positive as it goes through the zero value at the local minimum itself. Now the situation is reversed when you look at the behavior at the local maximum, because to the left of the point, as you move from left to right, the function is increasing. But its rate of increase is decreasing all the time, and at the local maximum point itself, the function is stationary. But then as you move through it and continue to move left to right, the function starts to decrease. So there the behavior is reversed. The sign of the derivative is positive to the left of it, positive but decreasing, and it goes through zero, and then to the right of it, the derivative has a negative value because the function is decreasing. Okay? So that difference in behavior characterizes the local minimum and local maximum point. Okay? At a point of inflection, the type of behavior you see is, well, this point of inflection, the behavior as you move left to right, to the left of the point, the function is increasing, and it's also increasing to the right of it. So it's got the same kind of behavior either side. Now, of course, there's another kind of mirror image version of that point of inflection, which isn't drawn there. But you can have a point of inflection going the other way, so just kind of the mirror image of that one. And to this one, either side of that point of inflection there, the function is decreasing. As you move left to right, the function is decreasing on the left, but it's still decreasing on the right. Here, the function is increasing on the left and increasing on the right. But the point is, it's displaying the same type of behavior on either side of the point of inflection. Okay? So that characterizes the point of inflection as compared to the other two, the minimum and maximum. Okay? So that difference in behavior is summed up in those bullet points there. But we can also characterize it by looking at the second derivative as well. Because for the local minimum, because you see, sorry, start with the local maximum. The local maximum, the derivative is positive to the left, it becomes zero, and then it's negative to the right. So that means the value of the derivative itself is decreasing as you move through a local maximum from left to right. So if the derivative is decreasing, that means the derivative of the derivative for the second derivative is negative. Okay? And the behavior is reversed for the minimum. As you move through the minimum, the first derivative is changing from negative to positive. So that means it's increasing. So that means the second derivative, which is the derivative of the derivative, the rate of change of the derivative, second derivative is positive quantity, when it's evaluated at the stationary point itself. Okay. And the value of the second derivative being zero is associated to the point of inflection. Okay. So there's a few examples worked out here. We'll have a look at these, and then we'll look at a couple of examples, more kind of realistic type questions from the notes. Okay. So in the first example here, we're dealing with the function y, which is x cubed minus x. And we'd like to locate and classify the stationary points of this function. Okay. So that's a two-step process. We first need to find the points, and secondly, need to locate them. So we find them by, first of all, obtaining the formula for the derivative of the function. So if the function is x cubed minus x, its derivative will be 3x squared minus 1. Okay, just using the rules for differentiating a polynomial. And that equation isn't too hard to find the roots of it. You're just moving the -1 and the factor 3 over to the other side, taking square roots. So you see it's got two solutions, plus root of a third and minus root of a third. So those are the two locations of the stationary points of this function. And we can classify what type of stationary point they are by looking at the second derivative. So the second derivative of this function is 6x, 6 times x. So when you evaluate it at the positive stationary point plus root of third, you're going to get a positive number. Okay, so it's just 6 times it. And you evaluate it at negative root of a third, you're going to get a negative number. Okay? So the positive one, x1 there, has to be a local minimum because the second derivative there is positive. And the second point, x2, is going to be a local maximum. Okay? And if you examine the graph of that function, you would see that behavior verified. Okay? So there's another example there in question 2, but I mean it's pretty similar. Pretty similar. We do a except here there's a point of inflection arising. So when you do the differentiation there, it comes out as 12x cubed minus 12x squared. So there's a common factor of 12x squared there in the two terms in the derivative. So you can factorize it like this. And then when it's factorized there, you can see what its roots are. You see the roots of x equals 0. Oh, I'm going to kill myself there. X equals 0 and x equals 1. Now at the point 0, if you go either side of 0, a small bit either side of 0, the derivative is always going to be negative, okay? If you go a small bit either side of 0, this x squared factor is always going to be positive. But going a small bit either side of 0, the x minus 1 is always going to be negative, okay? A small bit to the right of 0, you subtract 1, you're negative. Small bit to the left of 0, subtract 1, you're negative. So close to 0, the first derivative is always negative. So it has the same sign at both sides. So that means it's a point of inflection, given what we discussed earlier, okay? And if it's negative, it's going to be like this point of inflection here. It's going to be decreasing on the left and still decreasing on the right. You've got negative derivative on either side. Okay. The second one, x2 equals 1, comes out as being a local minimum, okay? Because when you evaluate the second derivative there, we would get a negative quantity. Okay, so is there any questions about that at the moment? We'll move on to some kind of more realistic applications of it now, do some better examples. But any queries at the moment? Okay, so let's go ahead and have a look at a couple of examples. And these examples are optimization type problems. Okay, so we attach meaning to the function, and it allows us to solve problems where we're looking for the optimal value of some quantity. So I'm going to try and do examples 9 and 10 here, or questions 9 and 10 in these end of chapter exercises. If you skip a few questions, if you look at the end of this set of questions, exercises 22 to 27, these are all some more optimization type problems. So there's another set of exercises there for you to try in the tutorials and that. 22 to the end, 22 to 7 there. Well, if we come back to question 9 for the moment, let's have a look at question 9. So question 9 talks about the dimensions of an athletics track or in a sports field or whatever. So here's a pretty awful sketch of a sports field. You're familiar with the idea. There's a large central field, which is we're thinking here of as a rectangle, and there's a running track around the outside, okay? Now, your standard athletics track has a perimeter of 400 meters, okay? 400 meters is the distance once around the running track. So we're talking about a shape which is 400 meters all the way around the outside. And we're saying it's made up of a rectangle, a central rectangle, and semicircular ends. Okay, so we got semicircular ends. And just given those conditions, one thing you might want to optimize is the total area that you have available in the field. Okay, because you'd want to be able to fit as many activities. Let's say in a, think of a track and field athletics. You got the track events going on around the outside, and you want to have as much space as possible, say, just roughly speaking, in the central field. So what is the dimensions of this that will maximize the central area? So the area in the rectangular field, how do we maximize this central area all the time keeping the external perimeter to be 400 meters? And with the requirement that these ends, I know they don't look like it there, but these ends be semicircles, okay? So we claim that this kind of problem we can solve using this idea of stationary points and whatnot, okay? So how to describe this? Well, we need to start attaching some variables or some names to the parameters. So there's two measurements which characterize the thing or define the thing. We've got the length of the rectangle, say, and the rectangle's width. Okay, so we've got these two measurements, W and L. Now, was that enough to define it? So W and L certainly define the central rectangle, and they do define the shapes here, because if these are semicircles, then that W has to be the diameter of that circle there. So the semicircle is determined by the value W, okay? Half of W will be the radius, so we'll just have this radius spoken out there. So it just takes these two parameters, L and W, to define the setup, okay? So we'll say the central field, let the central field have length L and width W. And we'll work in meters, since the perimeter constraint is given in meters. Then the perimeter P of the track is given by, so what's the perimeter? So what I want here is the perimeter is a function of two variables, W and L. So the perimeter of the thing, well, the perimeter is made up of these two long edges, L, so it's 2 times L, and then it's plus the circular bits at the ends. Now, if these are two semicircles, and they join together to give one circle, obviously. So we'll have a whole circle's worth of circumference to add to this 2L bit on the perimeter here. So the circle is diameter W, so the circumference of a circle is pi times W. Isn't it? So this should be pi times W. So that's the perimeter. It's given by this and constrained to be equal to 400 meters. Okay, so this must always total 400. Now the area of the central field A is given by, well, this is just the area of a rectangle. It's not too hard to write down. It's just the width by the length, isn't it? The area of a rectangle. Just the width by the length. Now this area isn't fixed. If you use if you adjust L, make L longer and W shorter, or vice versa, you can change the area. But we want to optimize the area. We want to make the area as large as possible. At the moment, it looks like the area is a function of these two variables, W and L. And we're able to change W and L, but we can't change them independently of each other, because they must always be linked by this perimeter constraint, okay? So if we rewrite this perimeter constraint in a suitable way, we'll be able to substitute it into this equation for the area here. So that's what we're going to do. So we're going to re-express the perimeter constraint. And we'll do it in this way. We'll say it's going to say W is 400 minus 2L over pi. So that's another way of expressing the perimeter constraint. So what that makes clear is that W and L aren't independent. W and L, there's a strict relationship that must hold between them. L can be anything you want, basically. But once L has a value, the value of W is determined by that formula. Okay. So we can get rid of this L. No, we can get rid of the W from this from our equation for the area and just replace it by this function of L here. Okay. So then the area becomes a function of the single variable L. So we have a recognizable function of a single variable, A of L, which is 400 over pi times L minus 2 over pi L squared. Okay. So what we've been able to do there is by encoding the perimeter constraint and substituting it into the area function, we've now got the area as a function of this single quantity L. And this automatically embodies the perimeter constraint. Okay. Now the question asked us to maximize this area. Find what's the maximum possible value of the area. Well, with this concept of stationary points we've introduced allows us to find out where the stationary points are and allows us to classify them into either local minimums, local maximums, or stationary points and so on. Okay. So we can say that the stationary points of L, stationary points of A, sorry, are the solutions to, well, its derivative, dA dL, which is 400 over pi minus 4 over pi L equals 0. Now, what solution does that have? It's true if and only if L is, well, in order for this to be 0, you better have L being 100. Yeah, 400 over pi minus 400 over pi to give you 0. So L has to be 100. L has to be 100, and the width, the associated width, W will be, W is 400 minus 200 over pi. So 200 over pi, whatever that is, as a value. So this is the location of a stationary point. We can confirm it's a maximum by looking at the second derivative of L, of A. So the second derivative, d2A dL squared, well, from the formula, it's minus 4 over pi, which whatever that is, it's certainly a negative number. So that confirms that this is indeed a local maximum. A maximum stationary point. Okay, so so that answers the question. If we want to maximize this central, if we want to maximize the area of that central field, we should make it have length 100 meters and width 200 over pi meters. And that will ensure then that remember the perimeter constraint is encoded by this expression here for W. So we know that the perimeter then of the resulting field will be 400 meters. Okay. Okay, that's good. So okay, any questions concerning that? And it's no surprise that 100 meters, you know, when they run the 100-meter sprint, that is just down one straight side of the running track. Okay, so it's no surprise that we see that number coming out. Of course, you know, that's a very simplified view. I'm sure there's more considerations that go into designing, you know, what the optimum, or, you know, what the best dimensions for an athletics field are. Obviously, there'll be other, you know, the perimeter track isn't a line. It has to be a certain width, has to contain so many lanes. So there's, you know, there's all different other things to take account of. But in that simplified view, it does kind of accord with what we observe in reality. Okay, then. So let's have a look at another problem, which again, I've tried to make related to the real world, and it has a nice kind of conclusion, which kind of accords well with our experience. So if you look at question 10 there, determine the dimensions of a cylindrical food tin of volume 330 milliliters that has minimum surface area. So, I mean, what's the thinking here? I guess the thinking here is that 330 mils is a sensible portion size, say for your can of Coke or whatever is 330 mils. So, and maybe the volume of a standard tin of baked beans is approximately 330 mils. So there's a thinking that that's a sensible portion size. Now, obviously, there are many different dimensions of tin that can contain 330 mils. What would be one of the main considerations that tell you which type of tin to produce? Well, I'm not claiming it's the only one, but one of the main ones would be you'd want to do it efficiently. You wouldn't want to waste aluminium in making the tin. You'd want to make the tin as efficiently as you can. So one way to do that will be to minimize the surface area. Okay, because if you're minimizing the surface area, then you're going to minimize the total amount of material you're using. You could arrange a tin which contained 330 mils that was like a huge tin. It was only like that tall, but it really, really wide. It'd be impractical, but you'd waste a load of aluminium making these huge circles for the top and bottom of the tin, which is really, really short. So you wouldn't want to do it. Wouldn't want to do it that way. So we think that we want to minimize the surface area. So can we find that optimal shape of tin? Okay, well, we're talking about a tin, so we need to be able to specify a tin and talk about its volume and its surface area. Okay, so there's a tin, cylindrical tin, so it's got a circular cross-section. Circular cross-section, so that tells you that one measurement you're going to need is the radius r of the cross-section of the tin. And the other measurement that's going to define the tin is its height. So it's got a certain height h and a radius r. So we'll consider the cylindrical tin of height h and radius r. Let's use the unit centimeters, because remember, The information about the volume constraint is given as a milliliter. So remember, a milliliter is a cubic centimeter. A little cube, 1 centimeter in every dimension is a milliliter. It's 1,000 of them in a liter. Okay, so we want to talk about the volume and the surface area. Okay. So we'll say the volume V and surface area S. Now these should be functions of R and H. R and H characterize a tin, so we should be able to express the volume and the surface area in terms of those. Well, the volume of a surface tin is the area of the circular cross section, which would be pi r squared, times the height. Okay, that's what the volume of a tin is. Sorry, of a cylinder. The surface area, well, there's three parts of the surface area. There's the circles at the top and bottom, and then there's the curved wall. So the circles both have area pi r squared, and there's two of those. So it's 2 pi r squared. They're the circular ends. The area of the vertical wall of the cylinder is the circumference of the circular cross section, which is 2 pi r, isn't it? 2 pi r times the height, h. Yeah, that's right. So the surface area is this, this expression here. So what are we doing with these two quantities? Well, the volume is held fixed. The volume, we want our tins to contain exactly 330 mils. So there's a constraint on the volume, and it's the surface area we want to optimize. Okay. So the volume constraint, and see, we got the same pattern happening here, is that the objective function, the one we want to optimize, at the beginning, it's a function of two variables. But having the constraint will introduce, you know, if you're just talking about any cylinder, R and H are independent. You can make it any size you want. But the volume constraint says, well, no, you can't make it any size you want. You can make it any height you want. But given the height, the radius will be prescribed in order to have the certain volume. Or you can make it any radius you want, but given whatever radius you want, the height is decided by the volume constraint. So the constraint introduces this, this relationship between the two. Now you got a choice about how you want to write it. You can either think of this as telling you what R is in terms of H or what H is in terms of R. I think we'll do it this way. So H is 330 over pi r squared. So that's equivalent. So that's just another way of writing the volume constraint. So that tells you that H is that given expression in terms of R. So this will allow us to eliminate the H from the surface area formula and just replace it with stuff depending on R. Okay. So now the surface area S becomes a function of one variable. Becomes a function of a single variable, so it's something we'll be able to apply our theory about stationary points to. So it's S of R. You've got your 2 pi r squared part, then plus 2 pi r multiplied by H, but H is this. So what's that? You're going to have 660 on the top, and the pi and the r disappear, and you've got 1 r on the bottom. So it's plus 660 over r. All right? 660 over r. So that's our function of a single variable. So that's the one, that's the surface area. That's the one we want to optimize. But we want to optimize it now by minimizing it, making it as small as possible. So we need the least amount of aluminium to manufacture the tin. Would be a sensible thing to do. Okay, so we seek the stationary points of this. Now, of course, there's some constraints in the variable here. The radius has to be the radius is a physical measurement, so it's a positive quantity. It can't be a negative quantity, and you know, we're obviously never going to talk about a tin of 0 radius because it doesn't make any sense. So r is restricted to be a strictly positive quantity here. So we seek the stationary points of this and their solutions to ds dr equals 0. So what is ds dr? Well, ds dr is 4 pi r minus 660 over r squared equals 0. Yeah? So you differentiate 2 pi r squared, you get 4 pi r. You differentiate 1 over r, you get minus 1 over r squared. And the 660 is still there, multiplying. Now we need to find the r that solved that. Now don't get too disheartened by the fact you've got r squareds beneath the line. Normally that might complicate things, but the right-hand side is 0, so you just multiply across by r squared. This becomes 4 pi r cubed minus 660 equals 0. And that can be solved without too much trouble, just algebraically. It's going to be 660 over 4 pi, and take the cube root of that. So there's only one stationary point. We should just confirm that it is a minimum. So we can look at the second derivative. d2s dr squared. So that's going to be, what's that going to be? 4 pi plus plus 660 over 2r. Yeah, 2r cubed. Now what is it about that number? Well, have I put the 2 in the right place? You differentiate it. No, sorry, the 2 is above the line. 2 is above the line. Well, I don't really care what that is, but the point about that is that is always positive. For any valid value of r, the radius, which is going to be a positive number, that is certainly going to be positive. And that confirms that the stationary point we found is a local minimum. So we have found a local minimum of the surface area. So if you make your tin, if you make your cylindrical food tin have this radius, then you'll be using the least possible amount of material to make it, supposedly. Now, what radius is this? Does this bear any relation to the Coke tins we know and love? Well, it's approximately 3.75 centimeters. If you think of your average drinks tin, a radius of 3 and a bit centimeters. I'm not saying that's what they are, but I'm saying it roughly. Yeah. Obviously, there's other considerations. You want something that is psychology. They want a can that feels like the right size should be in a typical hand. Other things. You want to stack them in a certain way. You want to make it efficient to be able to transport them. There are other considerations involved. But this one, at least now we know if it's, and of course they aren't pure cylinders, are they? They've got curved, the bottoms are concave. There's a much more complicated shape, but the principle is here. So this first approximation, if the tin is cylindrical, well, the tin of baked beans are pretty much cylinders. Tins of baked beans are. Making your tins with this radius and the associated height, then the height will be, the corresponding height will be 330 over pi times 3.75 squared. I don't have an approximate value of that, but I think when you work that out, that accords pretty well with what a tin of baked beans is. So that's the optimum value to minimize the surface area. Okay, any queries arising out of that or questions you'd like to ask? So there's a bunch of similar type questions there towards the end of the exercises. Question 22 says, of all the rectangles having a particular area, which one is the smallest perimeter? What's the answer to that? If you had to guess. Huh? Yeah. 22. Of all the rectangles having a particular area, which one is the smallest perimeter? Has to be a square. Because that's the only special rectangle. It'd be really weird if it was some non-square rectangle, wouldn't it? Surely it can only be the square. And similarly, of all the rectangles having a particular perimeter, which one is the greatest area? Kind of has to be the square, because that's a very strange argument, just because the square is the only special rectangle in a sense. But, you know, if you tackle those questions using the stationary point technique, you'll be able to confirm those answers. Question 24 is like a similar one to this food tin we've just done about, you know, something like packaging. You want to make a box. It'll have a base, but it'll be an open box, so no top. So it's just the base and the four sides. You want it to have a certain volume. What dimensions of it have the least amount of material in its construction? Now, if we did include the top, what would be the answer? Cube. Cube has to be a cube. There's no other special rectangular box. But the fact you're leaving off one of the sides of it means an open top box, that changes it. So the optimum construction is not a cube. Well, I don't know what it is, but it'll still be a square cross section, still be a square base, but it'll be, I don't remember, is it taller or shorter than it is wide? I can't remember. You'll have to work it out. You can work it out using these techniques. Question 27. You need a good sketch for question 27 to get you started. What does question 27 say? Question 27, it says you've got a straight river. Question 27, we've got a straight river and we want to build a pipeline across the river from a point here, A, to a point B there. And you're told what the river is. The river is half a mile wide. Half a mile wide, and the distance A to B is 3. B is 3 miles downstream from A. So you want your pipeline to run from here, A to B. So there's loads of ways you could do it. You could build the whole thing underwater. Oh, that's hardly the best way to do it, because putting pipelines underwater is difficult, especially a river which is half a mile wide. You're going to build the whole thing underwater. That'll be difficult. You could run the pipeline all the way down one bank and then straight across the river. But that's the longest possible pipeline you could use. So the question is there some better optimal solution? So what's the thing? Yeah, laying pipeline under the water is expensive, 25% more expensive per mile than laying pipe on dry land. So that's what's going to determine where the optimal point is. Okay. This one involves building the shortest section underwater, for sure. Going down the river straight opposite point B, and then going straight across the river. That minimizes the total distance under the water, but it also maximizes the total length of the thing. Obviously, it'd be silly to go past B and then come back. That'd just be crazy. But doing it that way is the longest possible pipeline. There'd be some intermediate situation, which would be going down one side and then across. So you're a little bit longer than strictly necessary underwater, but this pipeline going to this intermediate point and then diagonally across is shorter than this overall length. So what's the cheapest pipeline you can build given that? Okay. So again, now these questions aren't telling you explicitly what the functions are that you want to find the stationary points are. You have to construct those functions yourself from considering the problem. Obviously, for this one, any solution you have here, there'll be a symmetric solution, which is kind of the reflection of it. So going to this corresponding point first across the river and then down the opposite side. So you'll find two solutions, but they both kind of represent the same strategy, but they kind of mirror images of each other. Okay, so have fun with those questions, and bring any questions about them to your tutorials, and look out for the solutions on Moodle on that.